Constant questions. All right, so we're going to move on to question 4. All right, so question 4 says we've got, some reaction at equilibrium. Nope, no, not necessarily, but we know the KQ is 49.5. And we have some reaction, and it's a certain temperature. Okay, so 0.25 moles of hydrogen gas, another 0.25 moles of iodine, and they're placed in a 10-liter vessel, allowed to react. Question is, what is the concentration of each substance? What is the concentration of each substance at equilibrium? All right. So let's see here. So question 4. All right. Well, it looks like this is a situation where we're comparing initial and final concentrations. Looks a little tricky though, so let's see what goes on here. Okay. So rice, our reaction is our H2 and our I2, and that's in equilibrium with 2 hydrogen iodides. All right. So what do I know? I know that the concentration initially of our hydrogen is 0.25 moles for every 10 liters. So that means 0.025 moles per liter. And the same with the hydrogen, 0.025 moles. And I know I'm not starting with any hydrogen iodide. Now, I don't know how much I'm changing by. So I'm just going to say I'm going to reduce by X moles. So I know that it's going to shift and create products. I can tell because this is not sustainable in terms of equilibrium. I have too many reactants, not enough products, so it's going to shift to the right. So we're going to add X here. And, okay, so, oh, no, sorry, adding 2X, oops, because there's twice as many products in terms of molar ratio as each of these reactants. That was a close one. All right, so that means I've got 0.025, take away X, for the equilibrium concentrations of my hydrogen and my iodide. And my hydrogen iodide, or really it's iodic acid, is, 2X is the concentration. All right, so let's see what happens if we put that into our equilibrium expression. Equilibrium is our concentration of our products, the concentration of our reactants. So that means our equilibrium constant of 49.5 is equal to, I've got 2X squared, that's my hydrogen iodine concentration. And I've got this 0.025 take away X and 0.025 take away X, which is 2X squared over 0.025 take away X squared. Hey, what do you know? So that means, 49.5 is equal to 2X. I'm very tempted to try and square that and give us 4X squared, but I notice that these are both squared here, so that means I can really have this thing all squared, and then as an inverse operation, I can square root both sides. So the square root of 49.5 has got to be a little bit over 7, because the square root of 49 is 7.04. And that's equal to 2X. These guys cancel out entirely over 0.025 take away X. Huh, okay, that's a solvable problem now. I gotta multiply by my denominator, 0.025 take away X on this side, and multiply by it on this side. I'll distribute my 0.704 into both while crossing these guys out because they cancel. I get 2X is equal to this thing times 0.025, which is 0.176, take away 7.04x, that's equal to 2x. Huh, All right, then I guess I want to get all my x's on the same side, so I'm going to add 7.04x to both sides, add 7.04x. And that gives me 0.176 is equal to 9.04x. And I can divide both sides by 9.04. And then I get x is equal to this number, which is still my calculator, divided by 9.04. And it gives us 0.0195. Wait, what was x again? X was the change. Is the change in concentration of reactants, at least. So that means it's measured in moles over liters. Oops. Okay, that's fine. That's what x is. Were we asked what is the change of the concentration of our reactants? If we look back, we are asked what will be the concentration of each substance at equilibrium. So what we actually need to find, now that we have x, is what are these values. Okay, so my concentration of hydrogen gas is going to be equal to 0.025 molar take away x, which is 0.025 molar take away 0.195 molar, which is equal to 0.025, take away my answer, 0.00554. 0.00. I should really use my sig figs here, and notice I only had 3 decimals. I'm doing subtraction, so I'm going to call it 0.006 molar. And that's equal to my concentration of H2. All right, my iodine concentration has got to be the same, right? I don't have to do that calculation. So I'll just add that here as well, for the same reason. So I'll just make a little note there. Oops. I've got 0.06 molar, again for my iodine, because I'd have the same calculation, because my iodine concentration at equilibrium was still 0.025 take away x. Now the concentration of my hydrogen, or I guess my iodic acid I should say, is 2 times x, which is 2 times 0.0195 molar, which is 2 times 0.0195, which is 0.0390. That's equal to my iodic acid concentration. Okay, and those are our 3 answers. Okay, moving on, let's go on to question 5. Question 5 says the equilibrium constant for the Haber process reaction is 3 at a certain temperature. That's the equilibrium constant. Okay, so we're told enough ammonia was added to a 5-liter container. So enough. That makes me think that's going to be a variable. Question mark. Okay, such that the equilibrium in the container was found to contain 2.5 moles of nitrogen gas. And that's all we're told. We know at equilibrium there's 2.5 moles of nitrogen. And the question is how many moles of ammonia were put into the container. So maybe we should make a note about that. That question asks how many moles of ammonia were put into the container. Okay. So let's get started here. So question 5. We don't know much, so let's just see what happens. We know we're comparing some unknown initial condition to an equilibrium condition, so we can use a rice box. The reaction is the Haber process. And I have enough ammonia added. I have a feeling that's going to be my variable, but I'm going to just fill in what I can, and then we'll decide about what variable we need, if any. All right, so what do we know? We know that at equilibrium, the container was found. Okay, so we know that there was no nitrogen and no hydrogen added initially, but we know that there's 2.5 moles of nitrogen at equilibrium. Oh, 2.5 moles for every 5 liters, actually, so that is 0.5. Half of 2.5 over 5 is the same thing as 1 over 2, or half, or 0.5. Okay, so that means I know that I change my nitrogen gas concentration by 0.50. So I guess I should probably put X in here and let that be my variable for my concentration. Concentration of NH3 initially. And then we'll come back and we'll solve for the number of moles of ammonia, which is actually what we're asked for. So really it means we're going to take whatever X values and multiply by 5. All right, so if I know for every 1 mole of nitrogen, for every then I would, sorry, let me start again. I know I'm going to lose some ammonia, I know I'm going to gain some nitrogen, and I'm going to gain some hydrogen as a result. Because the only way I'm going to lose ammonia is if we're shifting and pushing this to create reactants. So if I know 0.50 moles for every liter of nitrogen gas are produced, I must have 3 times as many, because 1 is a 1 to 3 ratio. So 3 times 1.5 is going to be added for hydrogen gas. It's 1.50 moles for every liter. That means I've got 1.50 moles for every liter. And if that's true, I must have lost twice as many moles of ammonia as I did for nitrogen gas, as I gained for nitrogen gas. So that means I must have lost 1.0 moles for every liter. So my final value is X minus 1.0. Okay, I know all my equilibrium concentrations. I only have one variable because I know my equilibrium constant is 3.0, so I should be able to say my KQ is my concentration of products over the concentration of my reactants, and say, okay. So I've got 3.0 is equal to the concentration of X minus 1.0 squared over the 0.50 times 1.50 cubed, because it's raised to the power of 3. I should be able to simplify all that on the bottom and get it to be some relatively nice number. So I've got 0.5 times 1.5 cubed. Okay, so that means 3.0 is equal to X minus 1.0 squared all over 1.69. I'm going to times both sides by 1.69. Canceling these guys out. And on the left I get 5.06 is equal to X take away 1.0 squared. To undo that square, I will square root both sides. And I get 2 1/4. 2.25 is equal to X minus 1.0, so I can add 1.0, add 1.0. And so X is 3.25. And X represented a concentration of ammonia initially, so that means this is in moles per liter. Okay. Now, what were we asked for again? We were asked for how many moles of ammonia were put into the container. Well, I know there are 3.25 moles for every liter of ammonia. Concentration of ammonia initially. Okay, so to find the number of moles, I'm going to take that value, 3.25 moles for every 1 liter. And how many liters do I have? I have 5 liters. So 5.0 liters. My liters cancel, and it turns out I'm really multiplying my 3.25 by 5 to get 16.25 moles of ammonia initially. All right, making progress here. So let's move on to this last question here. Question 6 asks us to look at a reaction mixture. It's at equilibrium. And it contains, 0.15 moles of hydrogen gas, the same amount of iodine, and 8.70 moles of iodic acid. And that's in a 10-liter vessel. All right. Okay, this is one of these questions where it looks like we're adding a substance after we already know the equilibrium concentration. So we're adding 4.00 moles of HI is added, and then the system is allowed to reestablish equilibrium again. And then the question becomes, okay, well, what will the new concentrations of each of the species be? All right. So, this is a question where it looks like we can find our equilibrium constant to begin with. So we'll do that. So that means we've got this iodic acid concentration squared over our hydrogen concentration times our iodine gas concentration. And so what do we have here? Concentration of hydrogen iodide is 0.87 moles for every 10 liters. So it means it's 0.0870. And that's squared. And then I've got, so my concentration of hydrogen is 0.150 moles for a liter, or for every 10 liters. So that means 0.0150 moles for every liter. And that's the same for iodine. And I can just calculate that. I'm going to put that onto a calculator. 0.087 squared divided by 0.015 squared. You get 33.64. So KEQ for this reaction at this temperature is 33.6. All right. Now, looks like we're now disturbing equilibrium. We're going to add some more hydrogen iodide, and then it's going to regain equilibrium. Okay, so we've got some initial concentration, and we're going to ask about new equilibrium concentration. So that sounds like a rice table situation. Okay, so let's start by making one of those. So our reaction is hydrogen iodine mixed iodic acid at a 2-to-1 ratio. Let's just make that nice and clear. All right. Now, what do I know? I know I've got initial concentration of iodine, which is 0.015 molar, and same with hydrogen. And my iodic acid, I started with 0.87 moles. Okay, so concentration of iodic acid is going to be 0.870 moles plus 0.400 moles. That's all over 10.0 liters. So that means 0.87 plus 0.4 divided by 10 equals 0.127 molar. 0.127. And I don't really know anything else. But I know that because we increase the amount of iodide, we're going to lose, we increase the amount of hydrogen iodide at equilibrium. That means we're going to lose some of this stuff. But because I'm adding a certain amount in response of hydrogen and iodine, and I'm adding like less of this because of my molar ratio of a 1:1 to 2, I think I'm going to say I'm going to lose 2 parts of hydrogen iodide, and I'm going to add 1 part iodine and 1 part hydrogen. So it gives me 0.015 plus x, 0.15 plus x, and I've got 0.127 take away 2x. Okay, and now I can go back to my equilibrium concentration, our equilibrium constant, which is our concentration of our products, or the concentration of reactants, and say, okay, so 33.6 is equal to 0.127 minus 2x squared over, I've got the same thing for both of these terms, so 0.015 plus x squared, and I can square root both sides, and so I get square root, that's cube root, square root of 33.6, 5.80 equals 0.127 minus 2x over 0.015 plus x. Alright, so I can see it's going to be algebra. It's going to be a little gross here, but nothing really hard, just a little tedious sometimes when it comes down to this. But it's good to be comfortable with being able to solve for x when it's in all different types of positions and frequencies. Because what we're really doing if we're solving for x is solving for something that we don't know. And if we can't solve for things we don't know in real life, I mean, that's what problem solving often really is. So, okay, 5.8 times 0.15, so 0.015. I get 0.0869 plus 5.80x. Okay, so I'm going to add my x's to the left, so I get positive x's. And I'll take away 0.0869 from both sides. And cancel out terms that cancel. Alright. So I get 7.80 x over here, and that's all equal to whatever 0.127. Take away my answer is, which is 0.0401. And then I'll divide by 7.80, divide by 7.80, and I get x is 5.13 times 10 to the negative 3, or 0.00513. Now, what was my x representing? It was my change in concentration, so it's a concentration, so I should be able to give units of molar. Now, is that what I was asked? No. I wasn't asked for the change. If I go back to the question asks, what will the new concentrations of hydrogen iodide be? All right. So to solve this, I need to say, okay, well, my hydrogen concentration is going to be 0.015 plus x, which is to say 0.015 plus 0.00513 plus 0.015. That gives me, with the right number sig fig, 0.020 molar. I'm going to get the same amount for iodide. That's my hydrogen concentration. And it's also equal to my iodine concentration at equilibrium. Same calculation. And lastly, I need to find the concentration of my iodic acid, which is 0.127 take away 2 times x, which is to say 0.127 take away 2 times 0.00513 molar. And so that's going to be 0.127 take away 2 times 0.00513. And it's equal to concentration of 0.117 molar. And that's my concentration of hydrogen iodide at equilibrium. These are equilibrium. Okay. So that is all of our Rice table questions. All right. So let me know if you have any questions about any of these guys.